All right, learning targets, talking about LeChatelier's principle. Of course, we're going to outline the principle, all of the tenets that go with LeChatelier's principle. We're going to determine which way the reaction will proceed or shift, left towards the reactants, right towards the products, when certain stresses are placed on a system at equilibrium. We're going to look at these basic stresses, changing the amounts. Okay, you could either add them or remove them, the concentrations. Changing the temperature, which is really affecting endo-exothermic systems. And then changing the pressure of the ones that have gases in them, okay? And Boyle's law here with the decreasing, increasing volume idea. So that will affect the pressure. So we'll be looking at all of these as we are going through the notes. Let's see here, I gotta get my cursor back up over here and then we can press through. All right, so LeChatelier. Basic definition here, a system at equilibrium is disturbed by change in the temperature or pressure, concentration, one of the components. The system will shift its equilibrium position as to counteract the effect of the disturbance. So what does that mean? That means that it will shift back to that K value, that equilibrium constant, which happens to be a ratio between the established products over the reactants, the law of mass action. What does that mean? That means that you have the reactants making the products at the same rate as the products are making the reactants, and then you have the defined amounts at that point. Now, it's definitely dynamic if the process is continuing back and forth, but you get an established amount of each of the products and the reactants that are at that equal rate. Now we're going to look at the animation.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. LeChatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the hypothesis in which nitrogen and hydrogen react to form a bond. LeChatelier's principle tells us that if the pressure of the system increases, the equilibrium position shifts to a certain amount of molecules of gas and settle pressure. For the reaction is less occurring, energy is released to an amount of equilibrium. Increasing the temperature drives the equilibrium position and therefore the revolution, as the system dissolves into the equilibrium before the system. Increasing the temperature drives the equilibrium position to lose the excess energy upon the system. The system gets the equilibrium back into the system. Every unit is in the relative in the third of the center. And this way, as the pressure of the reactant is even more favorable, the pressure of the reactant
Okay, so what we saw there with our LeChatelier principle animation, basically showing like kind of like the balance there, where you had if you remove products, it makes more products. If you remove reactants, it makes more reactants. If you add in reactants, it shifts towards the products or proceeds towards the products. Once again, it's about getting it back to that K ratio, that law of mass action, the equilibrium constant ratio of the products over reactants. The amounts, definitely if you're adding and removing stuff, will change, but that ratio of the amounts will still be the same. The only thing that changes K, of course, is temperature, and we're going to go over that in just a minute as we get to, that particular effect on the stressing of the system. But right now, first of all, we're going to just deal with the basics of changing concentration. All right, so this is the best, easiest way I could outline it for you for concentration changes. The system will proceed to the opposite side from where the component was added. So if you add to the reactants, it's going to proceed towards the products. If you add to the products, it's going to proceed towards the reactants. It's going to go to the opposite side. If a component is removed, the opposite effect, of course, is going to go towards where you removed it from. It's going to replace what was taken away. So if it's removed, it goes to the side that it was removed from, towards that side. So if you remove product, it's going to go and proceed towards the product to replace the products and reestablish equilibrium. If reactant were removed, it would shift, it would proceed towards the reactants to replace the reactant that was now missing and removed. Now, a lot of the reactions have an equilibrium position. There's plenty of them out there. The one talking about making ammonia, that Haber process, that one's very important in agriculture because you need ammonia and fertilizer. So they manipulate it to make sure that they're getting the maximum output of the ammonia from their nitrogen and hydrogen reactants, their resources that they put into the reaction. So they manipulate the pressure, they manipulate the temperature to get the most large yield of the ammonia. And that's what you can do with equilibrium systems. If you know, you can manipulate them and in order to create a certain product. All right, phrasing. This is what we like you to use in terms of phrasing. There was once a push to get away from saying the word shift. I don't think it really matters, but told to say when adding gaseous or aqueous reactants, reactions proceed to the right towards the products. This is kind of the correct phrasing you want to use in the free response questions. Now, if you said it will shift right towards the products, I think that still is also an acceptable answer now. But there was a couple years ago a big push to not say the word shift, although it is by definition in LeChatelier's principle, so I don't understand what the problem with that would be. When adding gaseous or aqueous products, reactions proceed left towards the products, obviously. It's going to that opposite side again. So make sure though that you could say also reactions shift left towards the reactants. And of course it's going to do that in order to reestablish equilibrium, get back to that K value, that K ratio of the products over the reactants. That's a very important number and way of thinking about the system, is getting back to that ratio. When removing gaseous or aqueous reactants, the reaction proceeds left towards the reactants. Once again, you're going to the same side that you're removing from. When removing gaseous or aqueous products, reactions proceed right towards the products or shift right towards the products. Once again, going to the side that it was removed from, same side. So some phrasing here to use in free response questions. Way of talking about it. And in the previous lesson too, you kind of saw a way of looking at it in terms of K and Q, because when you add something in, now you've disturbed the equilibrium and now you have a Q value, and then it has to reestablish equilibrium and you compare it to K. And then of course, believe in the last notes it was showing you too, like K is greater than Q, it's going to go towards the products. K is less than Q, that's when it's going to go towards the reactants. That's a way of the way that the direction of the greater than, less than sign points. If you put K first, it has to be alphabetical. K versus Q, it will indicate for you, and you can think about Q as just the non-equilibrium values using that law of mass action, which is the products raised to the power of the coefficients in the balanced equation over the reactants concentration raised to the power of their coefficients in the balance reaction. When we disturb it, it becomes Q because it's not at equilibrium. Then we compare it to what the original K value is, and we can see which direction it's going in order to reestablish equilibrium. So the effects of changes on the system, looking at concentration here, let's take a look at this particular example. We'll go through them line by line, and you can tell me which way they would proceed here. So if I added in nitrogen here, adding in nitrogen, which way is it going to proceed? Towards the products or towards the reactants? Adding in is going to go towards the products. Now this also might be phrased as like adding in like 0.2 moles of nitrogen. They might say it that way too. So they could give it a numerical value as to how much they're adding to the vessel, to the system. So also realize that it might be a way that they phrase it. All right, so if we remove nitrogen, so adding nitrogen is going to go towards the products. Yes, opposite side. How about removing the nitrogen? We take it away, remove it. It's going to go and proceed towards the reactants. Very good, because it's going to want to make some more nitrogen. How about adding in ammonia? We add in some ammonia, which way is it going to proceed or shift? Should shift towards the reactants. So yes, adding this in should go towards the reactants. And if we were to remove hydrogen, take away the hydrogen here, which way is it going to proceed or shift towards? Definitely the reactants is going to want to replace the hydrogen as well. So basic gist of concentration, adding and removing. Once again, they can actually give you numerical values and say, you know, so-and-so added 0.25 moles of this to the vessel. How does that affect the equilibrium, system? They also might say, which ones are going to increase, which ones are going to decrease. So in that particular case, if we're removing hydrogen, obviously hydrogen is going to decrease. But if we're shifting to the left towards the reactants, that means the nitrogen is going to increase. However, if we're also shifting left towards the reactants, that means the ammonia is going to go down because it's going to be consumed. So they could ask, concentration questions of when we remove hydrogen, what happens to the concentration of nitrogen? Well, it's going to increase. What's going to happen to the ammonia concentration? Well, it's going to decrease because it's shifting to the left or going towards the reactants. And so the ammonia would be consumed. And it does that once again until it gets back to that established K proportionality of products over reactants. It's going to keep shifting until it gets back to that proportion. All right, here. So here, I guess I put in the arrows for you. There we go. All right, endo versus exothermic. We want to think about it in terms of where the energy is in the equation. Endothermic, energy is being absorbed, delta H is positive, all that good stuff. So it's going to be considered a reactant. Exothermic, energy is being released, delta H is negative. That means the energy would be on the product side. So try to position it in your head on either side or write it in if you need to. Like here, we're looking endothermic, if you have A plus B plus heat giving you C, you could have the heat here. You could also have it written as like kilojoules. They could give you a certain amount of energy, like they could give you like 100 kilojoules or something and write that into the equation as well. Exothermic, you would know the heat is going to be over here on the product side. Don't forget, you still need to remember delta H is negative. So they could also give you the reaction and tell you the delta H value, and you have to know based on the sign where to put the heat. So if it's negative, you put the heat on the products. If delta H is positive, you put the heat on the reactant side. Got to remember the delta H stuff. It definitely, like, stuff is going to start to really merge here now that we're getting into the later units of the year. And so we're going to keep adding and connecting different parts of the chemistry, and that's one here that will be connected. Now K will change depending upon the temperature, okay? When the temperature increases, the forward and reverse rates both increase due to the collision theory, because when you increase temperature, the particles' kinetic energy increases, so they're moving faster. That means they're going to collide more. So it actually does ultimately end up changing that products over reactants ratio, and that's why the K value is going to change. That has to do a lot with the kinetics here, not necessarily, anything else. All right, endo forward rate is higher, more products made, the K is going to increase. So looking at that, if it's endothermic, adding heat in, it's going to shift towards the products. So if more products are made, and we're looking at, K in general is products over reactants. If this numerator is getting bigger, okay, that means that the K is going to increase. So go back to that law of mass action. You don't have to put in all of the coefficients and stuff, but in general, if I'm increasing the numerator here, that means my K value is going to go up. So in general, it's products over reactants. Yes, when you're actually calculating it, you factor in those coefficients from the balanced equation. XO, the reverse rate is higher. More reactants are made and K decreases. Same idea here. Products over reactants. So if it's exothermic, you have heat on this side. Pretend it's just like adding something into the products. That means it would shift left towards the reactants. That means this denominator now gets larger. The reactants are now larger, so K is going to decrease. So keep that K equals P over R in your head. It's a really good way to kind of think about the ratio real quickly. So exothermic, reverse rates higher, more reactants made, K is going to decrease. Temperature, let's look here. The system will proceed to the opposite side from where the heat was added, just like before when we were adding in concentration or adding in, moles of something. Well, you add in heat and it's an exothermic, you're adding into the product side, so it's just going to shift left towards the reactants or proceed towards the reactants. All right, like here, down here, go that away, like it's adding in a product. When heat is removed, okay, same idea here. So say we decide to remove heat from the reactants. Well, it's going to want to replace the heat. So it's going to shift again towards the side that it was removed from. Now, if we were removing heat from the exothermic one, down here, if we removed heat, then of course it would shift towards the products to make more heat. We're acting exothermic in that case. Once again, wherever you're removing it from, it's going to proceed to that side and try to replace what was missing to reestablish that equilibrium. So you have to, first of all, decide, is it endo or exo, and where is my heat? Is it a reactant or product? Then you figure out which way it's shifting based on whether it's being added or being removed. Okay? All right, let's look here. Adding in heat to this reaction. Okay, so it looks like it's a reactant going to be endothermic in this particular case. Which way is it going to proceed as we increase the temperature here, which basically means you're adding in more heat? So which way will it shift or proceed? Towards the products. Very good. So we're adding in heat here. It's going to go this way towards the products. If it's going towards the products, what's going to happen to K? This is the only thing that changes K, by the way. Temperature is the only thing that changes K. So what happens to our K value? There's only two ways it can increase or decrease. Well, if we're making more products, remember P over R, so we're making more numerator, the effective K is going to be an increase. Good, yes, exactly right. A decrease in temperature real quick means we're removing it. So if we're removing heat from here, that means we're going to shift towards the reactants. If you're shifting towards the reactants, remember you're increasing the denominator here, so K would decrease in that particular case.